Dear students, we shall continue these numerical problems in electrostatic potential. You look at this problem. Two positive charges of 5 microcoulomb and 10 microcoulomb are placed 10 cm apart in air. Find the work done in bringing them 4 cm closer. So the problem is like this. There are two charges. One is 5 microcoulomb, another one is 10 microcoulomb. They are placed 10 cm apart. The question here is find work done in bringing them closer by 4 cm. So initially these two charges are separated by 10 cm in the air. If they are to be brought closer by 4 cm, how much work is to be done? This is the problem. You can get the solution for this problem on the basis of potential energy of a system of two charges. First you find the potential energy of the system of two charges when they are at 10 cm apart. When they are brought 4 cm closer, the distance between them will become 6 cm. Again you find the potential energy when the separation is 6 cm. The difference between these two potential energies will give you the work done in bringing them 4 cm closer. So you find initial potential energy of the system. You know the expression for potential energy for a pair of charges, 1 by 4 pi epsilon naught q1 q2 divided by r. So this is 9 into 10 to the power of 9, 5 into 10 to the power of minus 6, 10 into 10 to the power of minus 6 divided by 10 cm. So you do this calculation. So this will be 45 into 10 to the power of minus 2 joule. When they are brought closer by 4 cm, then this R becomes equal to 6 cm. Therefore, potential energy U2, this is given by 9 in 10 to the power of 9, 5 in 10 to the power of minus 6, 10 in 10 to the power of minus 6 divided by 6 cm means 0.06 meter. So you do this calculation. So if I do this, 9 into 5 divided by 6 into 10 to the power of minus 1. So this is 7.5, 10 to the power of minus 1. So you find the difference now. So this is point 45. This is 0.75. So work done in bringing them closer by 4 centimeters. W is equal to U2 minus U1. That means nearly 0.3 joule. So that is the answer. So you just you check these numerical values. You check these numerical values, and this is the procedure. So initially they are kept at a distance of 10 centimeter. If they are brought to be closer by 4 centimeter, then the work done can be calculated by following this procedure. You look at the next problem. A spherical conductor will have a potential of 600 volt when surrounded by oil of dielectric constant 1.5 and charged with 5 × 10⁻⁻8 coulomb. Calculate the radius of the spherical conductor. You look at the 7th problem. So here there is a spherical conductor. It is surrounded by, this is charged, it is surrounded by oil. The potential is given as 6000 volt. For oil, dielectric constant or relative permittivity, it is given as 1.5. It has a charge of 5 × 10⁻⁻8 coulomb. Now you are asked to calculate the radius of the spherical conductor. So this is a simple problem. You know that a charged spherical conductor acts like a point charge at its center. So for this point charge, the electric potential of spherical conductor it is given by the same formula for point charge, Q divided by R. You substitute all these values and do the calculation for this R. So this is 6000, 9 × 10⁻⁹, 5 × 10⁻⁸ divided by R. So if I find this R, it comes to nearly 0.05 meter. See, unless and otherwise it is specifically mentioned, we consider air as the medium. But in this case, specifically it is mentioned that spherical conductor is surrounded by oil of dielectric constant 1.5. So when a material medium other than air is there, this becomes the formula for electric potential. From that, R value can be found to be 0.05 meter. Look at the next one. This eighth problem. There are 2 point charges plus 10 nanocoulomb plus 30 nanocoulomb 1 meter apart in air. Find the potential at a point between them at a distance 0.8 meter from stronger charge. So, in the first part of the problem, you are asked to find electric potential at a point between them, which is at a distance of 0.8 meter from the stronger charge. So, between these two charges, at a distance of 0.8 meter from the stronger charge. So, here this is 0.8 meter. You are asked to find this electric potential. So, we consider this point to be A, this point to be B, and this is C. When this is 0.8, the remaining distance will become 0.2. So, this is 0.2 meter. So, electric potential at a point 0.8 meter from stronger charge. Vc, this is what you are asked to find. So, from the principle of superposition, potential at a point is equal to sum of potentials due to individual charges. So, Vca plus Vcb, that means 1 by 4 pi epsilon naught Qa divided by Ac, Qb divided by Cb. So, you do this calculation. 9 into 10 to the power of 9, both are nanocoulomb charges. So, 10 to the power of minus 9 is common. So, this is 10 divided by 0.2 plus 30 divided by 0.8. You simplify this one and do the calculation. It comes to be nearly 787.5 volt. So, at a point 0.8 meter from the stronger charge, in between the two charges, this is the potential. In the second part of the problem, you are asked to find the point between the charges where potential due to them are equal. So, you are asked to find a point between the charges where potential is equal. So, let us consider that x be distance from 10 nanocoulomb between the charges where electric potential due to the charges is equal. That means the potential at C due to the charge A should become equal to potential at C due to the charge at B. So, this is 1 by 4 pi epsilon naught Qa divided by x, 1 by 4 pi epsilon naught Qb divided by 1 minus x. You can strike off this common term. So, this is 10 nanocoulomb divided by x is equal to 30 nanocoulomb divided by 1 minus x. So, this nano 10 to the power of minus 9 can also be cancelled. So, 10 minus 10x is equal to 30x Therefore 40x is equal to 10, x is equal to 1 by 4, which means 0.25 meter. So from this charge at a distance of 0.25 meter, the potential due to them becomes equal. Understand this one? You look at this problem which was asked in July 2007. There is a spherical conductor of radius 0.2 meter having charge 4 nanocoulomb. So here there is a spherical conductor of radius 0.2 meter having charge 4 nanocoulomb. Find the potential due to this charged sphere on its surface, inside the surface, and at a 0.25 meter outside the surface. So here find V at the surface. Number 2, inside the sphere. Number 3, at R is equal to 0.25 meter outside, at a distance of 0.25 meter outside the sphere, outside 0.25 meter outside from its surface, at 0.25 meter outside from the surface of sphere. So this is the problem. This is a conceptual problem. This is the sphere. It is radius. You are asked to find the potential at the surface. So, electric potential at the surface, V is given by 1 by 4 pi epsilon naught Q divided by R. So this is 9 into 10 to the power of 9. Q is 4 nanocoulomb, 4 into 10 to the power of minus 9 divided by R is 0.2. So it is 180 volt. So 36 divided by 0.2. So it becomes 180 volt. So this is the solution to the first part of the problem. Next, what is the electric potential inside the sphere? Electric potential inside the sphere, V. Because in the theory I told you that potential at every point inside the sphere, it is a constant and it will be same as that on the surface. So whatever potential is there on the surface, it will be same everywhere. So it becomes 180. Next, the solution for this third part of the problem. Find the potential at the 0.25 meter outside from the surface of the sphere. That means from this surface here up to 0.25. So, electric potential at 0.25 meter from the surface. That means what about this distance r? So in finding this potential, this is the formula, Q divided by R. What is this R? It is distance from the center. So this is R plus 0.25. So 0.22 plus 0.25. It is 0.45 meter. So R means we have to take this value because the charge on the spherical conductor, it acts like point charge at its center. So from the surface, 0.25 means from the center it becomes 0.45. Therefore, this is 9 into 10 to the power of 9. This Q is 4 into 10 to the power of minus 9, 4 nanocoulomb divided by 0.45. So these terms can be cancelled. So it cancels. So this becomes a 900 by 45, which cancels 20 times. 20 into 4, 80. So this is the answer. So there is a spherical conductor having charge this much. You are asked to find the potential at the surface, inside and 0.25 meter outside the spherical surface. So these type of simple problems will be asked in the board examination. So just you should know this formula and you should know how to apply it. That is enough. So on the surface, this is the potential. Inside it will be the same. From the surface, 0.25 means from the center the distance will become 0.45. This becomes the potential. You look at this next problem. An electron is accelerated through a potential difference of 45.5 volt. What is the velocity acquired by it? So the problem is like this. Electron is accelerated through a potential difference of 45.5 volt. Find velocity acquired by it. See, in an electric field, along the direction of electric field, potential decreases. So, along the electric field, the kinetic energy will increase. That means the potential energy is going to be converted into kinetic energy. So, kinetic energy acquired by the electron is equal to potential energy. That means half mv square is equal to EV. So V is equal to EV divided by m under root. 2 EV divided by m under root. Now you just substitute these values. 2 into 1.6 into 10 to the power of minus 19. 45.5 divided by mass of electron 9.1 into 10 to the power of minus 31 kg. So you take these values and do the calculation. It comes to nearly 4 into 10 to the power of 6 meter per second. So along the direction of electric field, potential decreases. That means the potential energy of the electron decreases as it moves along the direction of electric field. This decrease in potential energy, it appears as increase in kinetic energy. Therefore, kinetic energy is equal to potential energy or work done in moving the electron. Therefore, this half mv square is equal to Q into V, that means E into V here. From this you can find the velocity of this electron. which comes to be 4 × 10⁶ meter per second. You see another one. A ball of mass 1 kg, 1 gram. Having charge Q is equal 10⁻⁻8 coulomb, moves from point A, whose potential is 600 volt, to the point B where the potential is 0. So here there are 2 points A and B. A, B. This potential at A, it is 600 volt. Potential at B is 0. Now, if the velocity of the ball at the point B is 20 centimeter per second. See here, this velocity is 20 centimeter per second. You are asked to calculate this velocity at A. So this is the problem. Here there is a ball of mass this much having charge this much. This ball is moving from one point to another point in the electric field. Here the potential is 600 volt, here it is 0, that means the electric field is in this direction. So this charged ball, it is moving in the electric field from one point to another point. While it moves here from here to here, that means where potential is 600 volt to potential 0, its velocity is gained to 20 centimeter per second. That means when the ball moves from here to here, this is the velocity. When the ball was here, what would be the velocity? That's the problem. So this problem is based on the principle of conservation of energy. See, when the ball moves from A to B, the total energy of the system will remain same. Further, whenever a charged body like this is in the electric field, it has got potential energy, and in this case also it has got kinetic energy. So the total energy at every point in this electric field is equal to sum of potential and kinetic energies. So according to principle of conservation of energy, total energy at A should become equal to total energy at B. That means the kinetic energy plus potential energy at A, this should become equal to kinetic energy plus potential energy at B. What is this kinetic energy? It is half m VA square. What is this potential energy? This is charge into potential at A. Here this kinetic energy is half m VB square plus potential energy is Q into VB. So to find this VA, this half m VA square is equal to half m VB square plus Q into VB minus VA. I take this term to the other side. Now you substitute for this m, VB, Q, VA and all. From this you calculate this VA. From this you do this calculation. So this comes to be 0.167 meter per second or 16.7 centimeter per second. That means here where the potential is 600 volt, this is the velocity. By the time it moves to this point where the potential is 0, the velocity has been increased to 20 centimeter per second. So these type of problems can be solved by using this principle of conservation of energy. That means total energy of the system remains constant. That means total energy of the ball at A will be equal to that V. So if you do this calculation for this VA on substitution, if you do the calculation for VA, it comes to be nearly 16.7 centimeter per second. In the CET examination, you can also expect questions based on the relation between electric field and electric potential. Okay, there is one problem. If electric potential is given by x square plus y, if electric potential at a point is equal to x square plus y, find electric field. Find electric field at the points of 2 meter and 3 meter. See, in electric field at a point, electric potential is this much. You are asked to find the magnitude of electric field at this point. See, when you are asked to find E by giving V, obviously you need to use the relation E is equal to minus dV by dr. Since E is equal to minus dV by dr, electric field is the negative gradient of electric potential. So actually this is a vector and this R is the position vector. So this equation, it can be written as minus of dV by dx I cap plus dV by dy j cap plus dV by dz k cap. So this equation it can be written like this. That means this is nothing but, this is the x component of electric field. Ex I cap, Ey j cap, Ez k cap. Like this. So, this x component of electric field is nothing but minus dV by dx, y component of electric field is nothing but minus dV by dy, and z component is minus dV by dz. So this V is given, this V involves x and y. So therefore, this Ex is equal to minus dV by dx. That means minus d by dx of this x square plus y. So this will become, differential of x square is minus 2x. So differential of x square is 2x. Because of this negative sign, it becomes minus 2x. At x is equal to 2 meter, this Ex will become minus 4 Newton per Coulomb. Similarly, Ey, this is minus dV by dy. That means minus d by dy of x square plus y. X square plus y. So differential of x square with respect to y is 0. differential of y with respect to y, it becomes 1, so it is minus 1. That is, at y is equal to 3 meter, this Ey is equal to minus 1 Newton per coulomb. Therefore, this electric field is minus of Ex I cap. That means minus 4 I cap, minus 4 I cap, and this Ey minus 1 J cap. So this is 4 I cap plus 1 J cap. This is the electric field. Therefore, the magnitude of electric field, this one. So it is nothing but root of Ex square plus Ey square. That means root 16 plus 1, root 16 plus 1, which is root 17 Newton per coulomb. So what is the electric field means you can write this equation or this one. What is the magnitude of electric field means this one. See, this is a relation between electric field and electric potential. This R being a position vector, you can find E like this. You can expect this type of problems only in NEET examination or JEE mains. As far as the board examination is concerned, usually these type of problems may not be asked in the examination. Similarly, in the competitive examinations, you can expect varieties of questions based even on equipotential surfaces also. So once in JEE mains this question was asked. So these are equipotential surfaces. This V is a 10 volt, 20 volt, 30 volt, and this angle is given as 30 degree, and this is graph of R. So this point is 10 centimeter, 20 centimeter, and 30 centimeter like this. In an electric field, equipotential surfaces are like this. Now you are asked to find magnitude and direction of electric field. Magnitude and direction of electric field. See, the relation between this potential and field is E is equal to minus dV by dr. See, this equation can also be written as this E is equal, dV is equal minus of E dot dr. You can write it like this. It is the dot product of E and dr. So this is minus E dr cos theta. What is this theta? It is angle between E and dr. See, these are the equipotential lines. That means along this line in the electric field, the potential is same. Here also it is same. Here also it is same. 30 volt. What is the direction of electric field with reference to equipotential lines? In the properties of equipotential lines, I told you that an equipotential line or equipotential surface, it will be always perpendicular to electric field lines. That means, if this is the equipotential line, obviously the electric field must be perpendicular to this equipotential line. This must be the direction of electric field. Because equipotential surfaces, they must be always perpendicular to electric field. So this angle is 90 degree. So here, if I consider E like this angle is 90 degree, this angle is 30 degree, so total angle will become 130 degree. So this is dV between two different equipotential lines. What is the potential difference? 10 volt. Between two equipotential lines, potential difference is 10 volt. And this electric field you need to find out. This dr, that means between two equipotential surfaces or lines, what is the separation here? 10 centimeter. So 10 into 10 to the power of minus 2. Cos angle between E and dr. E is like this, E is in this direction, dr is in this direction. So this total angle is 120 degree. So this will become cos 120. So this 10 is equal to minus E 10 to the power of minus 2, and this cos 120 is minus half. So from this you find the value of this E. So this is 10 to the power of minus 1, and taken this side, it becomes 100. So E becomes equal to 200 volt per meter at 120 degree. At 120 degree with R. So this is the magnitude of electric field, and this is the direction of this electric field. You can expect these type of problems in competitive examinations. So if you refer any CET book, you will find many of problems of this type. You try to work out those problems on your own, and in the next class I will start another topic, that is capacitors.